Okay, good morning. Have a good weekend? What's okay? You lost your what? You lost your phone. Oh, that's not good. I hope you find it. Okay, so today we're going to look at section 12.4. We'll look at another kind of product that we can do with vectors. And this one is a bit more complicated than a dot product. This is called a cross product. Okay, so again, let's say we got two vectors, A, A1, A2, A3, and vector B, B1, B2, and B3. When you do a cross product, we use the cross multiplication symbol. So A cross B, let me write down what it looks like, and then we'll talk about how we can get that. So it looks like this, A2B3 minus A3B2, A3B1 minus A1B3, and A1B2 minus A2B1. So right away you see this is far more complicated than the dot product, right? The dot product, we simply multiply the numbers together component by component and then add them together. Another very important distinction to make here is that the cross product gives you a vector. And dot product is a scalar. Okay, so this is a terribly hard thing to remember if you ask me. This is A2B3, A3 might B2. You can sort of see a pattern here, but it's, again, like I said, hard to remember. So we're going to use a trick called determinants. And you might have seen this before, but if not, that's okay, because I'll introduce that to you from the ground up. We'll start with a 2-by-2 matrix. So it's a formation of four numbers. And when you put straight lines next to, on either side of these four numbers, this means determinants. So by a show of hands, how many people have seen determinants before? Okay, about half, all right. Like I said, I'll introduce this to you as if you have never seen it before. When you see something like this, what you do is you multiply the main diagonal elements together, so A times D, and then you subtract away what you get when you multiply the other two numbers away, B and C. To make it more concrete, if we're looking for the determinant of 1, 2, 3, 4, then we multiply 1 and 4 and subtract away 3 times 2. And so we get 4 minus 6, that's negative 2. Okay, next let's see what happens when we do a 3-by-3. That means 9 numbers this time. let's say we have A1, A2, A3, B1, B2, B3, C1, C2, C3. Determinant of these 9 numbers that form a matrix is 3 by 3 matrix, 3 columns and 3 rows. So here's what we do. We work along the first row. So first we take this number A1. And then we mentally, or with a couple of things to help, block out the first row and the first column. So I take A1, and then I block out its row and its column. Then I find the determinant of what's left. Does that make sense? We take the number A1, block out its row, block out its column, take the determinant of whatever's left. Then we move to A2. And here's where things get slightly tricky. We have to reverse the sign of A2. So note the negative there. And just like last time, we block out the row and the column of A2, and then find the determinant of what's left. B1, C1, B3, C3. Then we move to the right one more unit. We get A3. And just like before again, we block out the row and the column of that A3 number, and then find the determinant of what's left. Okay, there are other ways to find the determinant, but for our purpose here, this is the way we're going to be using it, okay? And now we do 3 of these 2 by 2 we just did earlier. Here's A1 times B2, C3 minus C2, B3 minus A2 B1 times C3 minus C1 times B3 plus A3 times B1 times C2 minus C1 B2. Okay, is it clear which row, which column you block out? Yep. Okay, you pick a number, you block out its row and its column. Question? You're talking about the second line here? The one in the middle. This one? Okay, we haven't gotten there yet. This is not yet the cross product. That's setting up what we need to get a cross product. We have one more step to go before we get this thing here. Okay, so hang on 1 second. We'll get there, and you'll see that it will turn out to be the same thing. All right, so let's try this on a bunch of numbers and get used to how we do this thing. And then I'll show you how that allows us to find a cross product. Okay, so let's try this guy here. Okay, so here we got 1, 2, minus 1, 3, 0, 1, and minus 5, 4, 2. Work along the first row again. We take the number 1, block out its column, block out its row, take the determinant of whatever's left. Okay? The middle number here, we always change the sign. So it's a 2 here, but I want to write a minus 2. And that's a very important thing to keep in mind. Note the sign. Block out its column, block out its row. 3, minus 3, 1. We always read across first. 3, 1, minus 5, 2. And then the last one. Minus 1 times, block out its row, block out its column. 3, 0, minus 5, 4. Yeah. Which one? This one? That should be, that keeps its sign. Only the second element changes sign. Right? So this guy retains sign. This always changes sign. So let me make that clear here. But everything else, you keep the sign. Only the middle guy here gets his sign reversed. Okay, then let's finish this up. We get 1. 0 times 2, minus 4. Minus 2 times 3 times 2 is 6. Minus 5 plus 5. Minus 1 times 12 minus 0. And we end up getting negative 38. All right? Questions about this? Okay, now let's see how we can use this to do the cross product. Sorry about that. There should be A1, A2, A3, and B is B1, B2, B3. When we do A cross B, we form a big matrix and find its determinant. The first row of this matrix are the 3 special unit vectors I, J, K. The second row is the first vector in this operation. So A is the first one. We put whatever A looks like in the second row. And then the last row is the second vector in the operation. B1, B2, B3. And in the context of what we're doing here, you treat I, J, K as if they are numbers when you do the determinant. So let's find a determinant. First, we have I. So I sits here. And then I block out its column. I block out its row the usual way. That's a 3 here. Then I move to J, and again I change the sign of that middle number. Block out its row, block out its column. Finally, moving to the last one here, K. Block out its column, block out its row. We get A1, A2, B1, B2. Right? Okay, then we finish this up. A2, B3 minus B2, A3. I, right? Negative A1, B3 minus B1, A3, J. And finally, A1, B2 minus B1, A2, K. Compare that to what we wrote down earlier. Now you see they're the same thing, right? A2, B3, B2, A3, A2, B3 minus A3, B2, same thing. A1, B3 minus B1, A3. But the minus here actually reverses the order when you factor that in. So this matches up too. A1, B2 minus B1, A2. So this is a much easier way to find the determinant, find the cross product of any two vectors. This way, as long as you know how determinants work, you can always come up with the cross product of two vectors. All right, now I'm going to give you two vectors, and I want you to work on this and tell me what the cross product is. Take a couple minutes and tell me what the cross product is. And if you found it already, go ahead and find B cross A too. Okay, who's got an answer for A cross B? 54. How many people got that? Good, excellent. All right, so if you didn't get that, let me quickly show you how this turned out. Right, first row is always ijk. Second row is the first vector in the operation, 6, 0, minus 3. Last row is the second vector in the operation, 0, 9, 0. Then we go through our determinant process. I take out the first column, first row, determinant of 0, minus 3, 9, 0. Middle one, always change the sign, negative j, block out, block out. And the last one, k, block out first row, last column, 6, 0, 0, 9. So we end up getting in the I component 0, minus 27, positive 27. Middle one, 0, minus 0. 54 minus 0. Right? And you probably found out that B cross A turns out to be exactly the same thing with a sign reversed. And you can see if you go through the proper steps, here's what we get. This time I want B shows up first, so B goes into the second row, and A is the last one, A goes into the last row. And then everything you do is the same old determinant process. Just remember, always changing the sign of J. And last guy here, 0, 9, 6, 0. So we get negative 27 minus 0, nothing. 0 minus 54, so negative 54. Got that? Yep. Good. And what we found out here is always true. A cross B is always equal to the negative of B cross A. Always. So if you reverse, in other words, if you reverse the order of operation, you get exactly the same set of numbers, but the sign will be changed. In dot product, we don't have that problem. Right? In dot product, A dot B and B dot A give you exactly the same number. But here, things are slightly more complicated than a dot product. Okay, so that's how we find cross product. Any question about the determinant process and yeah?
Did you say that a matrix is equal to its determinant?
The matrix is not equal to its determinant. A determinant is a process, an operation you do to a matrix. Just like raising something to a power is something you do to a number. So, like if you say a number is equal to it raised to a power, that's not right. Same thing here. It's not the same thing, but something you do to it. And actually, we don't really care about the matrix in what we're doing here. It's just something that happens to help us to find a cross product. Other questions about the determinant? Okay, like I said, there are other ways to find a determinant of any matrix, but when you get to take a course in linear algebra, you'll learn all about it. For what we do here, that's the way, among the simplest ways to get what we want. Okay, now let's talk about geometrically what A cross B and B cross A give you. Geometrically, when you cross the two vectors, A cross B, what you get out is a vector that is perpendicular to both A and B. And its direction is determined by what's called the right-hand rule. So one of the most significant things you want to remember about cross product is that you get something that is perpendicular to both of the parent vectors you're crossing. Doesn't matter which way you cross, you always get something that is perpendicular to both A and B. So for example, we have A pointing down and B pointing up. The right-hand rule works like this. You take your right hand, not your left, right hand, okay? Stick your thumb out, and then with your other fingers, you sweep the first vector into the second one. So A cross B, A cross B. Okay, when you do that sweeping motion, watch where your thumb is pointing. That tells you where the resultant vector is. So you see, in this case, when I do A cross B, my thumb is pointing out of the page. Coming straight out at us. Right? A cross B. B cross A, now we got to kind of do a little bit of hand acrobatic here. You take your hand, right hand, stick your thumb out, and then you sweep B into A. And when you do that, my thumb is pointing into the page. You see that? So B cross A is into the page. Which means A cross B is the negative of B cross A, as we saw earlier. Right, out of the page and into the page are the same vector, but one is going, the only thing different is the direction. Coming out, going in, so there's an opposite, there's a sign difference between the two. Let's look at the three-dimensional coordinate system. Okay? So now you can see how these things are related. If I do I cross J, so this is a three-dimensional graph. Let's imagine I is my red pen and J is my black pen. Okay? Then I cross J by the right-hand rule is a vector. Notice it's perpendicular to both of those two vectors. And in this perspective, you can see that I cross J gives me a positive K. Try this on your own and find out what K cross J is. Use your right hand. And what do you get? Negative I. Excellent. Right? K cross J, we have to twist our hand around. And J, K swept into J, points into the page. In this case, I is coming out at us, so going into the page is in the opposite direction of I. Sorry. Okay? All right, so does the right-hand rule make sense? Yep? Okay, good. If you're left-handed, then when you're working this out, you have advantage. You don't have to stop writing. But if you're right-handed like me, well, we got to set a little bit of time aside. But that's okay. Not a big deal. So one time, I gave a quiz or something on the right-hand rule. And as I was walking around the room, I saw about a third of the students were writing with their right hand and using their left hand to do this thing. And of course, it was during a quiz, so I couldn't say a thing. But I wanted to. I so wanted to tell them the other right hand. So right hand rule is right hand. Okay? Also, if you cross the two vectors A and B, A cross B here, and you take the magnitude of the vector, you get a formula that looks a lot like the formula we have seen, one of the formulas that we have with the dot product. So here we have A cross B, magnitude of A cross B is equal to magnitude of A, magnitude of B times sine of theta, where again, theta is the angle between the two vectors. So notice that if A and B are parallel, if A and B are parallel, the angle between them is obviously 0, right? So you can see if A is parallel to B, then the magnitude of A cross B is equal to 0, right? So that's a very convenient way to check if you have two parallel vectors. If you just got two random vectors and the question asks you, find out if they are parallel. If you can do the cross product, find the magnitude of that. If it turns out to be 0, then those two are parallel. In addition to that, we could also use the magnitude of A cross B to find the area of a certain shape. So here I got two random vectors, A and B. What I'm going to do is to complete a parallelogram using sides parallel to A and B. And here's something that's quite interesting about it, about the vector's magnitude. It turns out that if you do the cross product, and then you find a magnitude, it turns out to be exactly equal to the area of the parallelogram. Right? So this shape here, the area turns out to be exactly equal to that. Okay, when you look at this and you go, how can that be? Let's find out why this is true. This is a very good exercise to find out why this is true. So let me draw the two vectors again. And actually, for convenience, let me draw A a little bit longer. First, we know the angle here between A and B is theta, right? And then I'm going to take a line from the tip of B, dropping it, and form a right angle with A. Let's take a look at that triangle here. This is the right angle. The hypotenuse, of course, is the length of B. Yep? And then, because this is theta, we know that this side must be equal to B sine of theta. And you can check sine of theta is equal to the opposite over hypotenuse. So if the opposite is exactly equal to that, when you divide by the hypotenuse, you end up getting sine of theta. Then what we're going to do is to rearrange this shape. I'm going to take this triangle and move it over here. And when I do that, this is what we just found. That's the magnitude of B sine theta. Right? And this is still A. I borrowed this part here from A, but then I put it right back. I give it back to A when I brought it back to the right side. So this is A. And so you can see we can rearrange that parallelogram by chopping off one side, the triangle from one side, and put it on the other side to make it a rectangle. Obviously, the rectangle area must be equal to the parallelogram area. We haven't taken anything away. We put back whatever we took away, which is equal to length times the width which we just saw in the last formula I gave you on the last page, is equal to the magnitude of A cross B. Right? Okay, are you convinced that this is indeed the area of the parallelogram? Yep, good. All right, so let's try this. I got 4 points here, and 4 points here. These turn out to form a parallelogram. We would like to find the area of that parallelogram. Let's make a rough sketch. It doesn't have to be very good, but just something that helps us visualize what we're doing. Here's A. Here's B. Here's C. And 0, 1, somewhere here. That's what we got. So a couple pages ago, we saw that if I can find out the 2 vectors that frame one corner of the parallelogram, I just do a cross product and find the magnitude. And look at here, you can use any combination of vectors you want. But what I can do is to find a vector here, call that A, find a vector here, call that B. You can choose to work with any corner. I happen to choose to work with the corner that's determined by the point A, but again, you can use any corner you want. All right, so A vector is D minus A, right? So positive 4, negative 2. Then the B vector gives me going from A to B, so I take B and I subtract A away, and I get positive 2 and 3. Now, all I got to do is to do A cross B or B cross A. It doesn't matter. We just want the magnitude, so it doesn't matter the order. But let's just do A cross B. So A comes into the second row, 4, negative 2. It doesn't have a K component, so that's 0. B comes into the last row, 2, 3. Doesn't have a K component, so it's 0. And now we do the cross product, A cross B. So the I component, block out, nothing. I get 0. J component, block, 0 again. K component, block, 12 plus 4, 16. So this is also equal to 16K. And K is a unit vector. Magnitude is 1. So the 16 determines how long this entire vector is. And it turns out to be 16. Yeah. These two? Okay, so A here is going from A to D, right? So I take D, and then I subtract A away. That tells me how many X units I need to give to A to put in here, and how many Y units I need to give to A to put in here. And then same thing for the others. All right, one last thing with the cross product. The 3D equivalent of a parallelogram is called a paralleloipiped. And so let me sketch what this thing might look like. So this is a three-dimensional shape that every single face is a parallelogram. So think of this as a rectangular box, but then you kind of deform it, give it some little bit of slope on each side. Turns out that we can find the area of this thing if you can find, again, 3 vectors at a corner. If you can go to any corner and you can find the 3 vectors that converge at that point, which we can do if you have the coordinates of all the points, just like we did in the last example. It turns out that to find the volume of this, it is equal to A dot B cross C. And you have to take the absolute value. So what you do is you do a B